Fun stuff, huh? Fun stuff? All right, chapter 12. So this class, our goal is to cover 4 chapters. Chapters 10, 11, 12, and 13. We're supposed to finish the book, all right? So we're halfway through the chapters at this point. Chapter 12, I think, is going to be somewhat of a welcome change of pace because, well, I don't know, welcome, but it has to do with integrals. And the chapter 12 is titled Multiple Integrals. So we are going to switch gears. Pretty much everything we've done up to this point, with the exception of a few things, has been derivatives, partial derivatives, and all of chapter 11 was partial derivatives. So now we go and talk about multiple integrals. And I thought I would start out the class by showing you an example of a problem we'll be able to do in a few days. We're not ready for it yet. But what I have here is, imagine you have a sphere, okay, or a solid ball. And you take this ball and you take a drill and you decide to drill out a hole through the ball, all right? And then you ask, like if you know the radius of the sphere and you know the diameter of the drill bit, then after you drill out the hole, can you tell me what the volume is that's left in the sphere of the ball? Does that make sense? But there's a little catch. I'm not drilling right through the center. I'm offsetting the drill bit. Okay, so I'm actually running my drill bit tangent to the z-axis, and I'm drilling through, so it's off-centered. And the question is, can we determine the volume of that? That is something you can't do that with anything you have up to this point. And the reason why is because the part that gets drilled out has a very weird shape to it. So let me show you here what I mean by that. There we go. Just the part that I drill out. So here's the sphere. And there's my drill bit. Okay, so my drill bit goes through, right? Drills through. The part that actually gets drilled out is, I'm going to take this out of here. I don't like that. We'll just look at the top half of it. The part that gets drilled out, can y'all tell that at the top it's got a little kind of dome to it, right? That's what makes this especially difficult, is the fact that that's just part of a little patch of the curved sphere. If this was a straight line through, we might be able to use some basic knowledge of geometry, but the fact that that's rounded makes this hard. So we'll be able to do this. This is actually out of chapter 12, section 3. We're starting with 12.1. Probably get to 12.2 today also. We'll see how it goes. All right? So that's where we're headed. But we have to start here. So a quick review of Calculus 1. That should say Cal 1/2. How many of you saw Riemann Sums in one of your Cal 1 or Cal 2 classes? Raise your hands. Riemann Sums? Okay? So if you have not seen Riemann Sums, some of this might look really weird to you, all right? I think it's important, though, that you have a basic understanding of the geometry that goes with the integral. So this is what we know from our calculus class. That if we had a curve, right, some function, and we wanted to know the area underneath it, we could approximate it by using rectangles and then adding up those areas, because it's easy to find the area of a rectangle, right? So we just add those up and we would get an approximate solution. And then how do we get a better approximation?
More rectangles.
More rectangles. So I could do more rectangles, right? This is too more rectangles. And so I have the actual area of this is 5.7506. If I do all these rectangles, I'm at 5.7516. So I'm pretty close to the actual area. And if I do more, you'll see that this number starts to approach the true area. And that's just because my error, the error that I have with these rectangles is basically approaching 0. And more and more and more, right? So let me go back here. How we constructed these rectangles, I don't know if you can tell from the picture, but right now the way I constructed these rectangles is I cut up the interval between, it looks like 0 and 5, cut it up into 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's what, 10 sections here? There's 10 equal sections. And the way I made the rectangles, I went to the middle of the first section, plugged it into the function, and then used that as the height. Then I went to the middle of the second section, went up, and got the height. This is called the midpoint method. In my classes, I don't talk about the midpoint method because it turns out that it doesn't matter how you do this. If you go to the right end instead, that means if you still break it up into 10 sections, and instead of going to the middle and up and going across, if you go to the right end point and up and across, right end point up and across, it turns out that it doesn't matter. Your answer still, as you get more and more and more, your error still goes to 0. Just look at, it didn't go, it's not going as fast. See how I'm not that close right now? But the whole idea is that we're going to let the number of these go to infinity. If you let it go to infinity, then it will get to the answer eventually. So you have like this midpoint idea. You could also do left point, and then there's another method called a trapezoidal. It all doesn't matter, okay? It doesn't matter if you break it into an interval. It doesn't matter if you pick the middle, left, right, or any point in between, because as that thing gets smaller, the point gets smashed in to one point, so it won't matter. Does that kind of make sense? Okay, so that's what we did. That's what we did in Cal 1 or Cal 2. I think I have. So we want to think about this. I apologize for the crappy drawings here, but I want to think about the picture I just showed you in a little more detail. See, what we're doing is we're taking the domain of the function, right, which is the x-axis. We're looking between A and B, and we're imagining having a little tiny change in x, little delta x here, little change in x. If we have a little change in x right here, then we want to measure the height of the function, which is f of x sub I, where x sub I is any point in here. This is where I would say midpoint, left point. Doesn't matter, pick any point in here, x sub I, plug that point into the function, and that will give you the height, and then the width of it is dx. So the area of this one sliver is, width times height, or height times width. So it's this times this, right? And that would give us the area of one sliver, and then we add them all up. And adding them up means doing a summation. And then we take a limit as n goes to infinity. So what happens is we get an infinite number of those in there. And that's the next line. This is the most important part right here. This right here, oops, the b should be up in there. The whole idea behind the definite integral is that f of x times dx is width times height, right? Width of the rectangle times height of the rectangle. And the integral sign means you're gonna be summing up n number of rectangles and then letting it go to infinity. So the integral means like an infinite summation. Is that all right? Okay. Now what we want to do is the following. Let's say we have a surface now. Okay? Say we have a surface. So this is a surface. It just looks like a little a little bowl almost. And what if I want to know the volume underneath that surface? So from the surface down to the xy plane, I want to know the volume. We're going to do the same method, except instead of doing little rectangles across, the interval A to B, what we're going to do is we're going to approximate the area under here by doing a bunch of, like, I don't know, what are those called?
Rectangular prisms.
Rectangular prisms. You call them parallel pipets is another name for basically a bunch of shoe boxes, or whatever you want to call it, boxes. So we're just going to do a bunch of these, and then add up the volumes of these, right? Add up their volumes, and that would give us the volume underneath here. And this would be an approximation, wouldn't it? So how would I get a better approximation? I just do more rectangles. So notice when I did that, I made them more narrow in the x direction. This is x and this is y. So I made them more narrow in the x direction, but I didn't make them more narrow in the y direction. But if I made them more narrow in the y direction also, then I would have that, right? And then my computer's probably going to freak out right now. If I go 40 cuts and 40 cuts, then I start to get even better, right? So the idea would be that we want to let the number of those go to infinity again, which means we're going to need an integral, right? We're going to need an integral to do that. So how are we going to come up with a formula? Let me go take this back to 10 because it'll probably slow me down with my computer. Just trying to remember what this is. Nothing. Oh, that's the surface above it. Why did it not stay there? Okay, so that's just the surface laid over it, so you can see that we have the little error, the little parts that are breaking out of the surface. So same fundamental principle, right, as we did in the Cal 1 and 2. So here's how we're going to do it. Our domain now is no longer a number line, right? Our domain is the ground. So our domain is the x, y plane. And what we want to do is take a little infinitesimal, like we did in the previous one, we did a little dx. This time we're going to take a little dx, dy. So a little change in x, a little change in y. We're going to take this little tiny patch, this rectangular patch, infinitesimally small. And then we're going to take any point that lies inside of that rectangle, and we're going to plug that point into the function. So here's that patch laying on the ground. I pick any point in here, plug it into the function. When I plug it into the function, that gives me the height of that box thing, right? And that right there, I need to find a formula for the volume of that. So the volume is, length times width times height. So you just do delta x, delta y, height. So that's this. And then we need to add them up, right? We need to add them up. But here's where things get different. The way we add the rectangles is like this. First, what we're going to do is we are going to add the rectangles across this front edge. Okay, so we're going to add across here, and then go to the next row over, and then add the ones behind it, and the next row over, and then add and add. So we're going to kind of like add across and move over, add across, move over, add across, move over. Does that make sense? So it's two sums. It's not just one sum. We sum across, right? But then we sum the other way, which means it's a double summation. And that's why in the formula, the volume, right, is going to be, sorry again for the crappy handwriting here, it's a double summation. You sum across first, you could do the y's first, or the x's, doesn't matter which order. You sum across, after you do that sum, then you sum across the other way. Which means, if we want to let the number of those go to infinity, we have to take a limit, and that means we're going to have a double integral, two integrals, instead of a single. That make sense? We're not going to get any more technical than that. Okay, that's all I'm, just want you to see visually what's happening here. That's just a repeat of the same thing. All right. So here's like the important, if you're going to take anything away from what I've said, here's the important thing. If you're trying to find the volume between a surface f of xy and the xy plane. Now remember, the xy plane is the same as z equals 0. That's the ground. So we're trying to find the volume between that surface and the ground over a rectangle. So on the ground is a rectangle. Then here are the integrals. There's two of them. Now let's see what's the difference between them. Now let's look at some of the notation. And I think next to this I'm going to draw a picture. So we have x here, let's do y here, let's do z here. So on the ground, I have a rectangle. Okay, and we're going to call this rectangle R. And then if I just take the stuff in the rectangle and push it up into the surface up here, not sure what it looks like. Just kind of making this up as I go. Okay, that's this rectangle pushed up into some surface. I'm just kind of making up what the surface is. Then if we want to know the volume underneath that, between that and there, then we need to do this. Also, this is A, this is B, right? That's our restriction on X, and then this is C, and this is D. So look at this notation. Our rectangle, the way we write that is we put in brackets AB, that's like a closed interval, and then cross, this does not mean cross product, it doesn't mean times, this is just a notation. Cross CD, and CD is our y coordinates. So this is how you represent a rectangle in two-dimensional space, is by writing it like this. So look at the way this double integral is written. Two integral signs, and then look at right here. You see that R? That's telling you that you're integrating over that region, that rectangular region on the ground. And what are you integrating? Well, you're integrating the function itself, right, the surface, with respect to what? With respect to A. What the hell is A? Area? Area, right? In all of our integrals in Cal 1, that little thing was usually dx, wasn't it? But that's because our little change on the ground, right, that little width of the rectangle was what? What was the width of the rectangle in Cal 1 or 2? It was dx, right? But see here, this dA is really dx times dy. Dx times dy is an area on the ground. That's that little infinitesimal little patch right there that's going to get plugged in. Does that make sense? So we have a new notation for it. Instead of writing dy dx, we just write dA, and we understand that that means we're integrating with respect to area. Is this all kind of making sense? Now, you can also rewrite this same integral, the same exact integral, this way, this is the same, but what's changed over here?
The integrals are flipped here.
These are flipped. Now notice, and I didn't point this out, I should have. Notice on this that the variable on the outside is x, right? And notice the integral on the outside, the limits of integration are a and b. And a and b are the limits on x. And then the inner integral is y, and that inner integral right there has limits cd, which match our limits of integration on y. Yes?
Are A and B always going to be related to X? Like, could you put A and B for Y?
You can't interchange them. What you can do is you can, what's happening here, you can switch the order of these, okay? But then these two switch, all right? But the x's have to stick with A and B, and the y has to stick with C and D.
So when you're doing this, you do the integral of the derivative of f of x. So like the top one, it'd be the integral of the partial derivative of f of x.
Let's do one. Let's do one. I think after we do one, you'll see how it works out mechanically. This is really just to show you like the notation that we use when we say we want to do the volume under a surface, right? But the important thing, let's not lose sight of this, is that this formula right here, and this right here, only work if what you're integrating over is a rectangle. This must be a rectangle. If it's not a rectangle, the formula is going to change. That's 12.2, I think. All right. So, I think I'm going to explain this as we do this example. So here we go. Let's find the volume underneath this surface on the interval 0,2 cross 0,2. Would you like to look at it first before we do it? See what it is we're doing visually first? No? Something like, nah, I don't need to see it. Okay, here it is. So first of all, this is the interval on the ground. Okay, that is what we're integrating over. That's our area. That's R, isn't it? Capital R. Now the surface is just sitting up here. Whoa. The surface is just sitting up here above our rectangle. And what we're going to do is we want to know only the volume above this, right? Up into the surface and below. So we're talking just about those points being plugged in. So only the stuff underneath that portion of the surface, right? And that means we're talking about that stuff. And let me bring out, I take the surface back out. That is what we're looking for right there. We want to know the volume of that piece right there. Okay? Make sense? All right, so how do we find it? Let's do it. So what I want to do is, I'll just say that the volume will be equal to the double integral over the rectangle of the function of the surface with respect to area. Right? That's what it'll be. Now for us, we have a lot of this information. So let's start out with the integrals. Can we put limits of integration on these integrals? What are they? 0, 2, 0, 2. Now remember, this is your x, right? And this is your y. It's always given to you in that order, x then y. Now they happen to be the same numbers, okay? So you can't get this wrong for this example. But this is going to be 0, 2, and 0, 2. Now, out here, I'm supposed to have either dx, dy, or the other way around, right? This is where this matters. Whatever you put on the outside, these numbers have to match up with that, right? And then this dx has to match up with that. But again, since they're the same, we can't get it wrong, right? So do you all want to do dx or dy?
Yeah.
You want to go dx first, then dy? Just like this? Okay, so then now I just need the function in here. Okay, so what is the function? 16 minus x squared minus 2y squared. Okay, that is the setup, all right? Questions? Just to make sure you understand this. If this was 5, what would change?
The 2 on the left.
To 2 where?
This.
This would change to a 5. Okay, just make sure you got that. All right. Okay, now, how do we do this? Well, the way we look at this, since we have a double integral, is we look at this right here as being what we'll call the inner integral. And then the other one, what do you think we call that? The outer one, right? I won't label it, because I think it would be kind of weird to label it. But we start with the inner integral. That's where we're going to begin. All right? So watch how I write this. I'm going to continue it over here because I need some more room. This is equal to integral 0 to 2. That's this. Okay? Now, in brackets, let's figure out this inner integral. What I have to do is I have to look at this expression, and I need to find the antiderivative of this expression with respect to what variable? X. That means that x is the variable, and y is going to be considered to be a constant here. All right? So this is the opposite of partial derivatives. We're going backwards. We're taking antiderivatives. So what is the antiderivative of 16 with respect to x? 16x. Okay, so we have 16x here. Okay, what is the antiderivative of x squared? Sorry, negative x squared would be minus x cubed over 3. I'm going to write that as 1/3 x cubed. And then what is the antiderivative of negative 2y squared?
Negative 2y squared x.
Yeah, you can write it different ways, but negative 2y squared x. Because negative 2y squared is a constant. And the antiderivative of constant is the constant times the variable. Right? This all make sense? Now, that's the antiderivative. But it's a definite integral. It goes from 0 to 2, doesn't it? So now, back from Cal 2, you put this line, I think we call it the evaluation bar or something like that, and then you'd put like 0 here and 2 here, right? Now I'm going to do this a little different. I'm going to put x is 0 and x is 2. Now the reason I put x is 0 and x is 2 is because we have more than one variable here. So we need to know what variable are we replacing with 0 and 2? X, right? Because we integrated with respect to x. You don't want to mix it up and be replacing the y's with it. See, back in Cal 2, it didn't matter because it was always x. Now we're going to have x, y, and then after 12.3 and 12.4, we're going to go to triple integrals. You have x, y, and z, so you have to know exactly what you're plugging in for. Right? So, all right. Let's keep rolling here. I've got this, right? I shouldn't have put equals. Sorry about that. I want to close the bracket. That's my inner integral, right? That's my inner integral. And then I still have here dy. That's the outer integral. Okay, equals integral 0 to 2. Still working with the inner integral now. Bracket. Now, how do we do these definite integral things? Which one do you plug in first?
Top one.
Top one. 2 goes in here first for x. And then after you do that, you subtract 0 being plugged in for x, right? So that means I'm going to have two things. I'm going to have whatever I get when I plug in 2, and then whatever I get when I plug in 0, and then I'll be done with that, and then I'll still have dy out here. So let's replace x with 2. What do you get here? 32 minus 8 over 3. That's 1/3 times 8. And then minus
4y squared.
4y squared. So just replaced all of our x's with 2's. All right, now place all your x's with 0's. Oh, great, that's awesome. 0. All right, now we keep going. This is equal to, let me just clean it up. I don't need the blue anymore because I've got an answer here, right? Oh, I should put these two together. Those are both numbers, right? It's 32 minus 8/3.
88/3.
88/3? Okay, so I have 88/3 minus 4y squared. And I'm integrating that with respect to y. And now you are back in Cal 1 or Cal 2. This is Cal 2. Can we just say Cal 2?
Yes.
Great, okay. We're in Cal 2 now. Right, there's just like a basic integral in Cal 2. So the antiderivative of that with respect to y would be 88/3 y, and then minus 4/3 y cubed. And we're going to evaluate this at y equals 0 and y equals 2. And we plug in. So when we plug in, we're going to get something here, and then take away something here. Let's see. What is it?
48 minus 0.
48. Oh, you already got this whole thing? It came out to be 48?
Yeah.
Okay, I believe you. 48 minus 0. So if you plug in 2 here and you simplify, trust that that's 48. So what's the final answer? 48. Now, this is a unitless measurement here, because we don't know if things are measured here in feet or inches or miles or whatever. But whatever the units would be, this would be like 48 cubic inches or something. That would be the volume. of the solid below that surface down to the ground. What do you think? Pretty okay? All right. Okay, how about this one? Why are my inputs showing up? I think I'm in the wrong mode. Hold on. Okay. Let's look at this one first, before we do it. This is an interesting one. So our rectangle, you see our rectangle, I used a different notation for our domain. You all see that? Just a different notation. That's the one you're probably more familiar with. So x is between 1 and 2, and y is between 0 and pi. So x is between 1 and 2, y is between 0 and pi, and that's the ground. Now the surface that we're plugging into is that surface right there. Weird looking thing, right? Can you tell here, we got something going on that's a little different. I'm going to kill the light just for a moment. Can you tell that we got something interesting here?
Part of our surface area isn't, it's not under.
Yeah. Part of the surface is underneath the region that we're integrating over. So do you remember in Cal 2 what happened? Like in Cal 2, if you were asked to integrate sine x dx on the interval 0 to 2 pi, what would your answer be?
0.
It would be 0. Because the sine curve on 0 to 2 pi, you get area here which is considered positive, and then area here which is considered negative area. And so if you actually do this antiderivative, you get 0, right? So that means that in Cal 2, anything below the x-axis was counted as negative, and anything above was counted as positive. And that's exactly what happens here. Anything that's below is going to be counted as negative volume, and anything that's above is going to be positive volume. Does that make sense? But we're going to be looking here at the total at the end of the day, the positive, and then you add to it the negative, and what's at the end, what do you get as your total volume, all right? While I've got it up here, what's nice in Cal 1 or Cal 2 is that if I wanted to know just this, I could just integrate from 0 to pi instead, right? And then I could get that, right? Here, that's going to be very difficult to figure out where this surface is above the xy plane. It's a challenging question. And you can tell it's kind of along this little ridge right here. That's where it's above, but okay, we're not going to do that. All right, so here's the range. So when I plug in, and let me just get the volume in here. And let me take the surface out. So there it is. We got part of it is above, part of it is below. What's the total net? Is that what we'd say? The net volume. Let's do it. So I set up my double integral. The volume will be equal to the double integral over the rectangle R of the function of xy with respect to area. As you see, as we move through chapter 12 and 13, we're going to be doing pretty much integration from here on out. You're going to see that this little d whatever is going to change as we move from one section to the next. Sometimes it's integrating with respect to area. Other times we'll be integrating with respect to arc length or with respect to some vector field. I mean, this thing is going to continually change as we move through the class. So that's why I really want you to understand right now, dA stands for area. The A stands for area. All right, let's set it up. Okay, limits of integration. How do you want to do this?
y then x.
You want to go 1 to 2 first? And then you want to go 0 pi? Okay, if you do that, then your order of your d whatever is now set. So what's the outer one have to be? dx, and what's the inner one? dy, okay. And then we are going to be integrating y sine of xy, like that, right? That's ugly? Is that what you said?
Yeah, that's ugly.
What, the inner integral seems ugly?
Yeah, because you got that xy thing, and then you have multiplication.
You have a y out here.
Yeah, that's wild.
So you do 5 parts.
That's not too bad.
Integration by parts
Because
is
it's
what
a
it would take for
constant.
that, right? And that would take integration by parts.
In this case, would you want to switch it then, like do the dx then dy, so then whenever you do it, the first integral, you could treat y as a constant and be easier? Or would it
That's
just be
an
the
excellent question. Let me, go ahead, what was yours?
Question, the sine of xy, don't we have to, isn't there something we have to do to that before we can integrate it?
Well, x, on the inner integral, the x is going to be like a constant.
Yeah, isn't a constant times the argument, don't we have to do something gross with that?
When we're integrating, we will have to account for the constant. It's like, that problem, the inner integral right now really is like, may as well be like this.
Yeah.
Okay, so to do this, we have to do integration by parts, which means we have to choose one of these to be our u and one of them is the dv. And I would use that for u, and when we do this as dv and integrate it, all we have to do is make sure we put like -1/4 cosine 4y, like just to compensate for the 4 in there. So if we replace that with x, right, this is going to be -1/x,
Okay.
right? So what do y'all think? Do you want to, oh, sorry, no, the question was, we can do that, or if we'd like, we can do the opposite order.
That sounds easier.
And this time we will be integrating with respect to x first, right? And if I integrate this with respect to x, then y is a constant, and we don't have to worry about integration by parts. At least not on the first integral. Maybe the second integral, the outer one, we might. Right? We might have to, but this is a great question. We know that both, the order doesn't matter. We can do it this way or this way. We were told that in the very beginning, because we said the integrals are interchangeable. You can flip them. But sometimes one is easier than the other. I actually like this one because I would prefer to integrate that with respect to x rather than y. Y'all agree? So let's do this one over this one. So Milton beat me to it. He stole my thunder there. I was going to ask you the same thing. All right, so we're going with this option instead. So this is going to be equal to integral 0 to pi. And now I start bringing in my inner integral. My inner integral. I'll just go ahead and write it down. Integral 0 to 2 y sine of xy dx. And then
Should be
dy.
1 to 2.
Pardon?
Is the
Oh, 1 to 2.
Yeah.
Yes, thank you. 1 to 2. Okay, there we go. So this is your integral 0 to pi. Now, what is the antiderivative of y sine of xy?
negative cosine xy.
Yeah, so let's do this first. Y is just a constant, right? So it comes for the ride. So that's going to be here. Now what's the antiderivative of sine of yx with respect to x? You said negative cosine of xy. What's missing? There's something missing there.
Negative 1.
Be over, that's over y. You have to do, so if you ever have trouble with this, just do this on the side. Sine, y is a constant, right? So it's like, how would you find the antiderivative of that? this would be negative 1/3 cosine of 3x. Again, because you have to compensate for the fact that when you take the derivative of this, you're going to eventually have to take derivative of the argument, which is going to be a 3, but you need the 3 to go away, so you scale it by 1/3. And the negative's there so that we can get a positive sign. Make sense? So the antiderivative here was this, but what am I missing?
Over x.
1 over y. 1 over y, because y is the constant in the problem.
Oh, doesn't the y's go away then?
Then the y's are going to cancel. I think that's, I don't know if
Yeah.
you had already canceled the y's. Okay, so I didn't want to jump that far. Okay, so these y's are going to cancel, all right? The good news, you can check it, right? Can't you just check this? Like, take the derivative. What's derivative of negative cosine of something? Positive sign of that. Then take derivative of what's inside with respect to x, and you get a y to pop out. And that's what this is. What we're doing here is what's called partial integration. It's like partial differentiation, partial derivatives, but it's integration. So you're holding one thing constant. All right. I still need to throw some more stuff in here. What do I need here? A little bar. And we're going to go where? 1, 2 here. Oh, what is 1 and 2? We're doing x, right? X equals. And then on the outside, dy. Okay, let's do it. Equals integral 0 to pi. And then on the inside here, we've got to plug stuff in. We've got to plug in, and then subtract, plug in, and then be done, and then dy. Okay, what happens when we plug in 2 for x? Let's get negative cosine of 2y. And then what happens when we plug in 1? Negative cosine of y. Which equals integral 0 to pi of cosine y minus cosine 2y dy. Right, I just made the double negative positive, moved it out front. All right, you feel okay taking the antiderivative of that? Yeah, see, looks like we're not going to need integration by parts at all. So, let me see here. Antiderivative of cosine y is sine y minus antiderivative of that. What's the antiderivative of that?
1/2 sine.
1/2 sine 2y. And then I'm going to evaluate that, and y equals 0 and y equals pi.
Is this where you have to split it up in pi over 2?
Nope. Just plug in here. What's sine of pi?
0.
Sine of 2 pi.
0.
0. So that's 0 when you plug in pi. And then when you plug in 0?
0.
0. So all of this literally for nothing. Which means that the volume that was above this is equivalent to the volume that's below, even though it wasn't symmetric. Could y'all tell that didn't look symmetric? It was like weird shaped. But it does turn out that the volumes are equivalent. Just for this particular problem, it worked out that way. Yes?
So if they weren't equivalent, like what would it look like then? Would that mean
Then we would have got a positive answer or a negative answer. If it was a positive answer, that means there was more volume above than there was below. If it was negative, then it would be more below than above. Does that answer your question? Yes?
So why are we doing the net and not doing it like we did before with
It's much more challenging to do just the part that's above. Because what you would have to do first is figure out, let me bring up the picture and we'll try and visualize it a little bit. If we go back to this picture, yeah. Now, there's some weird looking stuff on this picture, and it's just the limitations of my computer. I asked the computer to graph a certain region for me, and it almost graphs it like point by point, like plugging points in and evaluating. And if I want to get a really accurate picture where everything looks really smooth, then I have to have it compute a whole lot of points, but it slows the computer down. So I do just enough to get a picture, but let me see how many points I have it plotting here. Maybe I can go a little more. I'm afraid to. Where are my plot points? I'm only having to do 30 points. Let me just do 60. I'm going to see if that freaks the computer out. That's better. Does that look a little better? Or can you even tell the difference? This edge right here got a little bit better. Let me do. See if I can bring it to its knees. It's thinking. Yeah. It's doing quite a bit of work right now. Oh wait, hold on. Well, I forgot to hit the volume button. Now it's doing quite a bit. We were just sitting here, it wasn't doing any work. It was doing just fine. Okay, it's actually running now. So let's see. You can do it. See what I'm saying? I had to pick a number of points that made it.
So we know that the volume of the top and the
There it
bottom
is.
are equal because it's zero. But
Because
what's
it's
the
zero.
actual volume, like what's the number of the top? Like, you
That,
know,
I think that's what we're asking right now.
okay.
Okay, so I was trying to first get a decent picture to look at. So there's a decent picture. Isn't that nice and smooth now? Y'all see that? So here's what we'd have to do. We would have to figure out this arc right here. Then it looks like this, this, and then the back goes like that, right? So what we would need to do is instead of integrating over the rectangle, where was it, from 1 to 2, and then from 0 to pi, instead of integrating over this rectangle, we would need to integrate over this instead. Does that make sense? But the problem is that's not a rectangle. And this section is about integrating over rectangles. Okay, the next section is about integrating over shapes that are not rectangles. So we're not ready for this. There's a way to do it. But even though we can do it later, it's this right here. What is that?
It's a quarter of a circle.
Well, is it a circle?
I mean, like,
Isn't that where the surface, the original surface is 0?
Yes.
Okay, so what was the original surface? Y sine of xy. I would have to solve this equation of two variables, right? I'd have to solve this. I'd have to figure out what would make this 0. Now, of course, if y is 0, we're done, right? So really, I need to figure out where sine of xy is 0, right? Which means that x times y has to be what?
Sine negative, inverse sine of 0.
Any multiple of pi. No? Is that too much?
No, I think you do.
Yeah, that makes sense.
Any multiple of pi. Because if this multiplies to be, if these two multiply to be any multiple of pi, then what we have is sine of any multiple of pi is 0, right? So now if I solve this for y, then this is going to be n pi over x. And basically this is your, like a reciprocal function. Like if n is 1, let's say, then this is pi over x, isn't it? And if you graph y equals, well, let's not do pi over x. What's 1 over x look like? right? So pi over x is just that stretched out. So this right here is probably y equals pi over x. And then, so we have like, you see where I'm going with this? It's challenging. We could probably do it in the next section, but we won't even do this. I don't think we'll do this one. All right, so that's how we figure out the positive part, but it's messy. Let me go back into my code and change this back so next time I run this, I'm not sitting here freaking out. Trying to. So this is just Fubini's theorem, which is, I've already kind of told you this. It just says that so long as the function is continuous, I mean nice and smooth, and we're integrating over a rectangle, that the order of integration doesn't matter. All right? The order does not matter. That's a theorem though. I mean, like, we can't just take that like for granted. Somebody has proven that theorem. Fubini has proven that theorem. So on this one, we want to verify it, which means we want to integrate it both ways and see if we get the same answer. I think I'm going to skip this. All right, this is a special case. All right, let's say that we have a surface. Okay, this is our surface function. But let's say that it's equal to g of x times h of y. That's our special case. So let me give you an example. I want you to take a look at this. Say we have a double integral, and say in here we have y sine of xy dA. All right, is this the special case? Do we have a function of x times some other function of y? I shouldn't have shown you that, but I'll give you the answer. No, it's not. Because look, this right here by itself is a function of y, isn't it? But this right here is a function of x and y. They're mixed together. What would qualify, so this does not work, what would qualify is if this was like that, then we are in a special case where you have your y function is separated from your x function by multiplication. You basically have two factors. So there aren't any y's and x's mixed together within some function. Does that make sense? If that happens, if this happens, then what you're allowed to do is break it up into two separate integrals. This is the only time you can do it. And this is multiplication between the two. So let me put some limits of integration on this one. Let me take this example. Well, you know, I'm probably going to give you an example on this. Yeah, there we go. Let's just do this one. So find the volume under sine x cosine y on this rectangular region. So I'm going to go right to the integral. Both my limits of integration are going to go from 0 to pi over 2. And this right here doesn't matter if I go dy dx or dx dy. Right? This doesn't matter because these are the same. Now, is this the special case? Yes. This is the special case. You know what? Let's do something, because I think it'll be more clear if I do this. Let's change this to pi. Can we do that? Just change that to pi. And that way we can really distinguish between the two. So this one goes now from some 0 to pi here now, right? The inner one, because it's with y. According to the special case, I am allowed to, at this point, look at this as the product of two integrals. The first integral is the one with x. So what would I put here? From where to where? 0 to pi over 2. And then in here, sine x dx. And then this one, 0 to pi. And then cosine y dy. So what you do is you just just ignore this, crank this integral out. That'll give you a numerical answer, right? And then you crank this one out, it'll give you a numerical answer, and then you multiply the two answers. So let's do them. Antiderivative of that, negative cosine x, evaluated x equals 0 to x equals pi over 2. I'm going to get that answer, I'm going to multiply it times antiderivative here, which is sine of y, evaluated y equals 0 to y equals pi. See, that's why pi over 2 would have been better, because what's this integral going to be over here? You plug in pi, we're going to get 0 and 0. This is all going to be 0, and it's going to kill everything off. But do you understand how that special case works? Okay, that's all that's important there is how it works. This doesn't happen often. Okay, but when it does, just be aware of it. It saves you a lot of time. All right, some properties of double integrals, things that you should just be aware of. We don't want to assume these things are true, but luckily for us, everything kind of follows just exactly the way it did in Cal 2. If you have two functions, two surfaces being added or subtracted in a double integral, you can break it up into two double integrals. So if there's addition or subtraction, you can split it. If you have a constant in front of a double integral, the constant can come out. If you have a surface that is hovering above or equal to some other surface, then you should expect that the volume under that surface should be bigger than or equal to the volume under that surface. Does that make sense to you?
Yeah.
I mean, this is kind of obvious, but now, what about if you have two surfaces and you're trying to find the volume between the two? Well, it's just like we did in Cal 2. Just like we did in Cal 2. Yep. If you have, in Cal 2, if you had a function here, f, and you had some function below it, g, and you wanted to go from a to b, and you wanted to find the area between them, then you would do the integral from a to b of f of x, which would be the upper function, minus g of x, which is the lower function, and then dx. That's the way we did it in Cal 2. Same exact property here. If the f function is above the g function, okay, so if that's above, that surface is above the other one, then you subtract the two, and because it's subtraction, you can split it into two integrals, and that'll represent the volume. So this is the picture of what's happening. You have a rectangular region on the bottom. You have a lower surface, G. You have an upper surface, F. And you're trying to find the volume between those. Same picture. That's it. That's it for that section. Feel okay about that? So when it comes to double integrals, integrating over rectangles is the easiest one because it's very straightforward. You can reverse it. Everything flows great.
So we always be given the points of the rectangle, these domains?
Yes, the domain. Well, yes. Now, as we move forward, not necessarily. Like the one, remember the problem I started with the ball, we're going to cut a hole, right? That one? Just to give you kind of a heads up of how we're going to do that is, let's just take like the top of the ball. Like here's like the axis that comes through, that, and we cut out this piece over here, right? And it came down like that and drilled through. Okay, on the ground, what shape is on the ground?
Circle.
You have a circle on the ground, right? So what you're really trying to find is the volume below this surface, right? There's a surface right there. You're trying to find the